We will now move on and talk about the synchronous generator or synchronous machine. This is the last part of chapter 3. Let's start with some basic review. So the synchronous machine in fact has got two windings, and they have one armature winding, which is a three-phase winding that is located in the stator. Then it has a field winding that is located on the rotor, and which is of course fed then with DC voltage. And also the armature is laminated because the armature winding, which are housed on the armature, in fact, it see a time varying flux. As the rotor rotates, it generates the EMFs, and it has a frequency which is given by the omega E, as you see here. And we have then the relationship that omega E is equal to P divided by 2 times omega M. P is the number of poles in the machine, while omega M is the mechanical speed. This shows a relationship between the electrical rotation and mechanical rotation. So normally steam turbine driven machines are in fact high speed generators, and to get 50 Hz such a generator, they run typically at 3000 RPM in a two-pole machine. On the other hand, the hydro machine is a low speed and have salient pole construction, which basically have many poles, or we can say many pole pairs. The rotor of the salient pole machine has what they call a damper windings at its pole face. Here you can see one salient pole, and the field winding is located here surrounding the ferromagnetic iron material, and then you have some damper bars out here. So the salient form, as you can see here, the damper bars are short-circuited, and it's actually the same as a squirrel cage on an induction machine. The basic function of these damper bars is basically damp out transients. Normally both the field winding, like from the flux created by the field winding, as well as also the three-phase rotating flux. And it can also be the rotary motion of the rotor, are all at the same speeds. So during transit you have got currents in these damper bars, and they intend to damp out any transient which actually is occurring. On a cylindrical rotor, the field winding is housed in slots, as I try to show here. So the slots have wedges, which are not very clear on this, but it keeps then the windings in place. So actually the field winding is placed then basically in the slot in the cylindrical pole machine actually. Now, just to get a good feel on the sizes of such a synchronous machine, we can have this example here. For example, consider a 210 megawatt machine, and what is the typical parameters of such a machine? MVA of this machine is 247, so you can actually calculate the rated power factor based on this information. And in addition, the rated voltage is given to 15.75 kilovolts, and the rated current is roughly then 10 kiloamps, so a little bit above 9000 amps. And it's of course a 50 Hz machine. When I say then the rated current, that means that there is the maximum continuous rating of the armature current. So, but it doesn't mean that the current is not above, but it can only tolerate like say 10% above this, and only for maybe 10 minutes maximum. So the maximum continuous rating is around 10 kiloamps from this. Similar with the field, you get a rated current on 2006 amps. So with the rated current here means that the current which flows in the field winding in order to get the rated voltage under loaded condition. That is full load condition or the rated load conditions. The rated voltage of the field is around 310 volt, and the efficiency can be very high. In the case around maybe 98.55%. But this is of course on the generator we're talking about. It's not the turbine and so on. So one important thing that you should take note of is that when you talk about field current, rated current 2600 amps, that's under load. However, it's much less than with no load conditions. It maybe just be like a half of the rated current during no load condition, and you want to keep the rated voltage. When it comes to temperature and limits, we have three main limits, and those are the armature current limit, and secondly is the field current limit, which located on the rotor. Then we have the core end heating, the end of the rotor. So we will, in the end of the rotor, we have a winding here, and especially in what we call an under excited operation, we can have higher axial flux. So these are three important heating currents that we need to take care of in the system. Here is a synchronous generator named Obera. We have already been seen on the transformer side. It's owned by Skagerrak Kraft, and this generator has a rated value of 103 MVA with the voltage rated 11 kV, and the stator current is on 5406 amps with the 50 Hz. Here you can see the size, and here is the weights. It's a 12-pole machine, and the weight complete stator is 102 ton. Weight complete rotor is 148 ton. And it's a 3.4 meter in diameter inside this stator. Here you can see the stator armature windings coming up from the stator. It's also called the verbal bar. Here is the rotor with the 12 poles surrounding it. And you can see also a fan below here pushing air through the air gap of the machine. Here is a cutaway view of a total enclosed machine, and you can see the sizes here, but of course here you have the stator, and you have an air gap between stator and rotor. Then we have the rotor here. It's located down on a bracket, and a bearing is holding it in a position, and also total weight of it. Then we have the shaft in the middle. We have heat exchanger cooling the air down, surrounding the machine. So what kind of function does the machine have? We have already talked about it, but it's magnetical. The rotor pores are electromagnetic that produces the flux density. It induces the voltage in the generator. We also have function of mechanical. Transfer the torque from the shaft to the field through the air gap coming from the turbine side. Carries the poles, gives inertia that is beneficial for the grid stability. So that's a mechanical function. And thermal, because it's spinning, it acts as a fan and helps with the cooling side. So that was the function of the rotor. The function of the generator, as we talk about the magnetic, the stator core guides the magnetic flux around the coils inside the stator. For the mechanical part, the stator core fixates the coils winding, and also the core translates the torque to the support structure, the stator support. Also thermal, it has the ducts in the stator core, guides the cooling air, and the core conducts the heat away from where the losses occur. So here you can see from the top and down, so the air is typically pushed down here and through the stator. Here you can see the stator, called the stator tooth, the iron tooth here, and this is the rubber bar placed in here. So this is the copper. Here goes then the current in these copper bars, and this is the iron part. It's also then closed with a wedge in the end here. And we typically have temperature sensor between the rubber bars here. Looking from above here, we can of course see the rotor and the stator, and this is the magnetic flux lines. So you putting pole field, and we have a magnetic flux lines in the rotor going into the stator over the air gap. Magnetic flux, and then we have the air gap here between, and of course teeth, as I already talked about. This is slots for coils, as I mentioned, for the rubber bars. There are two types of rotor topologies I already mentioned, and we use so-called DQ transformation to actually look how it can be modeled. We'll come back to that. The cylindrical rotor has just what to say. We have a D-axis and a Q-axis. The D is direct axis and the Q is quadrature axis. So they are 90 degrees displaced from each other. And for the salient pole rotor, we have they are not equal as it is in the cylindrical rotor, and this is due to the design of the rotor. And also the Q-axis, you can see here, is then in between the D-axis in this regard. We'll come back to more on this later, but just remember it's a D and Q-axis when we work here. And that is just a mathematical tool to be possible to model this as it rotates the rotor in regard to the stator field. So it's two fields that's counteracting actually. Here you can see the rotor from the synchronous generator, Åbyra. And as I said earlier, if you want to increase the EMF, you can increase the B, spin faster, increase the number of poles. So that's all if you want to increase the voltage. Here is one of the field winding are taken down from the rotor, and you can see it lays here. Here is then this is copper surrounding. And then we have damper bar in the end here. It's if you want to calculate then the speed from the pole pairs and the hertz, we can use this formula here, as I said in the beginning. So we have omega is 2 times pi times f, and that means it's rotates with a 314 radian per second when we have 50 hertz. To find, for example, the RPM speed of this machine, we can use this formula. And in Åbyra we have 12 poles, and it's a 50 hertz. So that means with that number of poles we have a 500 RPM speed. So depending on what kind of individual poles you have, you can get different types of speed. And as I said, then the high-speed steam turbine typically have a few poles and a high speed. But for hydro machines, we have more on the more poles to get a lower speed. I already mentioned this, but the damper bars consist of short-circuit copper bars embedded in the pole surface. So it's located here, damper bar slots. So it will reduce currents acting to restore synchronous operation when you have transients in the system. Here's also a drawing and how they are interconnected between the poles. This is the pole surrounding the rotor. Now here back to Åbyra, and now it's some photos from this, and we can see here we take a photo inside the machine, and here is the air gap, and here is the rotor pole, how it's mounted, and the air gap is around 25 millimeter. Here is the excitation system. So we have brushes here and plus and minus pole, and then we so the excitation currents around 1065 amps at 250 volt, the rated value as I talked about earlier. However, they had a problem with it, so they had some of the brushes was not working as it should, so they had some kind of damages to this system. This is actually a typical problem that you have brush system excitation systems. So here is a static excitation system, as they say. Here you can look at the stator when it's mounted, and you can see now, but inside here, this is the durable bars coming up surrounding in the stator. So here is an visualization of the rotating machine, a 4-pole machine, and you can see how the magnetic flux line are distributed. And this is done in console. Here is a 2D snapshot of Åbøra, where we have the magnetic flux density lines. So this machine now is under full load. So you can see this red part here is magnetic field is very high, almost 2.5 Tesla at this part. So here is the stator teeth, the damper bar, and this is the pole core, rotor ring, and the rotor winding. And here is the sensor is located in the rubber bar. And this is the core, stator core, as it says. So this is made of iron, and this is copper surrounding the winding. Let's look at the cooling system in such a machine. So here we have, we can look into the machine from the side, and we have the heat exchanger here, and we have cooling air, the blue one coming out, cold air, that is drawn over windings. This is the rubber bar. Here is the rotor, and this is the air gap where you can see the yellow here. The cold air is drawn over here through the fan, down into the air gap and through the stator, and it's then heated as it goes through the ducts and out to the heat exchanger. And the same is also below. So this is the cooling circuit or the heating circuit for this system. And we have then sensors, as I said, located around in these rubber bars between them. And we have also sometimes sensors in the stator yoke, as you say, the core out here, mounted into the machine. Here you can see the pointed out the stator yoke where it is, and also the stator teeth here.